Section: Introduction. The challenge of embedding images into generic features that can be used for various purposes in computer vision has been a long-standing issue. Initially, methods were based on handcrafted principles, like SIFT, but with the advent of deep learning techniques and the increase in data scale, end-to-end training became possible. The pursuit of generic feature embeddings is still relevant today, as gathering valuable annotated data for many specific tasks is challenging due to the required expertise or the cost at scale. Currently, it's common to pre-train a model for a task with abundant data and then use a part of the model as a feature extractor. There are several approaches to this, including supervised methods that build on classification or text-image alignment, which allow for the training of robust feature models to facilitate downstream tasks. On the other hand, self-supervised methods that build on the transformer architecture have gained significant attention due to their high prediction performance on downstream tasks and the intriguing ability of some models to provide unsupervised segmentations. In particular, the Dino algorithm has been shown to produce models that contain explicit information about the semantic layout of an image. It's been observed that the last attention layer naturally focuses on semantically consistent parts of images and often produces interpretable attention maps. Leveraging these properties, object discovery algorithms like LOST build on top of Dino. These algorithms can detect objects without supervision by gathering information in attention maps, effectively opening up a new frontier in computer vision. DINOv2, an improved version of Dino, provides features that allow tackling dense prediction tasks. These features have led to successful monocular depth estimation and semantic segmentation with a frozen backbone and linear models. However, we noticed that DINOv2 is surprisingly incompatible with LOST. When used to extract features, it delivers disappointing performance, only on par with supervised alternative backbones in this scenario. This suggests that DINOv2 behaves differently than Dino. Our investigation revealed the presence of artifacts in the feature maps of DINOv2 that were not present in the first version of this model. These artifacts can be observed qualitatively using straightforward methods. Interestingly, applying the same observations to supervised vision transformers exposes similar artifacts. This suggests that Dino is, in fact, an exception, while DINOv2 models match the baseline behavior of vision transformers. In this work, we aim to better understand this phenomenon and develop methods to detect these artifacts. We observe that they are tokens with roughly 10x higher norm at the output and correspond to a small fraction of the total sequence, around 2%. We also show that these tokens appear around the middle layers of the vision transformer, and that they only appear after a sufficiently long training of a sufficiently big transformer. We found that these outlier tokens appear in patches similar to their neighbors, meaning patches that convey little additional information. As part of our investigation, we evaluate the outlier tokens with simple linear models to understand the information they contain. We observe that, compared to non-outlier tokens, they hold less information about their original position in the image or the original pixels in their patch. This observation suggests that the model discards the local information contained in these patches during inference. On the other hand, learning an image classifier on outlier patches yields significantly stronger accuracy than doing so on the other patches, suggesting that they contain global information about the image. We propose the following interpretation to these elements. The model learns to recognize patches containing little useful information, and recycle the corresponding tokens to aggregate global image information while discarding spatial information. To test this hypothesis, we append additional tokens, that we call registers, to the token sequence, independent of the input image. We train several models with and without this modification and observe that the outlier tokens disappear from the sequence entirely. As a result, the performance of the models increases in dense prediction tasks, and the resulting feature maps are significantly smoother. These smooth feature maps enable object discovery methods like LOST mentioned above with the updated models. As shown in Fig. Most modern vision transformers exhibit artifacts in the attention maps. The unsupervised Dino backbone has been previously praised for the quality of local features and interpretability of attention maps. Surprisingly, the outputs of the subsequent DINOv2 models have been shown to hold good local information but exhibit undesirable artifacts in attention maps. In this section, we propose to study why and when these artifacts appear. While this work focuses on alleviating artifacts in all vision transformers, we focus our analysis on DINOV2. Artifacts are high-norm outlier tokens. We want to find a quantitative way of characterizing artifacts that appear in the local features. We observe that an important difference between artifact patches and other patches is the norm of their token embedding at the output of the model. In Fig. Left, we compare the norm of local features for a DINO and DINOV2 model given a reference image. We clearly see that the norm of artifact patches is much higher than the norm of other patches. We also plot the distribution of feature norms over a small dataset of images in Fig. Right, which is clearly bimodal, allowing us to choose a simple criterion for the rest of this section. Tokens with norm higher than 150 will be considered as high norm tokens, and we will study their properties relative to regular tokens. This hand-picked cutoff value can vary across models. In the rest of this work, we use high norm and outlier interchangeably. Section Summary. Embedding images into generic features for computer vision has been a long-standing problem, with early methods relying on handcrafted principles before the advent of deep learning. Pre-training models for specific tasks and extracting features has become common, but the DINOV2 algorithm, while successful in dense prediction tasks, exhibits artifacts in feature maps that hinder its performance. These artifacts, characterized by high-norm outlier tokens, can be mitigated by appending additional tokens to the token sequence, resulting in smoother feature maps and improved performance. Section. Outliers appear during the training of large models. During the training of large models, we've noticed some unusual occurrences, which we refer to as outliers. We've made a few observations about these outliers while training a model we call DINOV2. Firstly, these outliers, which are high norm patches, start to stand out from the rest around the 15th layer of our 40-layer vision transformer, VIT. Secondly, these outliers only start to appear after about a third of the training process. Lastly, when we examined models of varying sizes, we found that only the 3 largest models displayed these outliers. Interestingly, these high norm patches seem to appear where there is redundant information in the patch. To confirm this, we compared the high norm patches with their 4 closest neighbors right after the patch embedding layer. We found that these high norm patches are very similar to their neighbors, suggesting that they contain redundant information. This redundancy means that the model could potentially ignore their information without negatively affecting the image representation. To better understand these high norm patches, we decided to examine the patch embeddings for different types of information. We used 2 tasks for this: position prediction and pixel reconstruction. We trained a linear model for each task and compared the performance of the high norm patches with the other patches. For position prediction, we trained a model to predict the position of each patch in the image. We found that the high norm patches were less accurate than the other patches, suggesting they contain less information about their position in the image. For pixel reconstruction, we trained a model to predict the pixel values of the image from the patch embeddings. Again, the high norm patches were less accurate than the other patches, suggesting they contain less information for reconstructing the image. However, when we evaluated the high norm patches on standard image representation learning benchmarks, we found that they held more global information than the other patches. Based on these observations, we hypothesize that large models that have been sufficiently trained learn to identify redundant patches and use them to store, process, and retrieve global information. While this isn't necessarily a bad thing, it's not ideal that it happens within the patch tokens, as it leads to the model discarding local patch information, which could potentially decrease performance on dense prediction tasks. To address this, we propose adding new tokens to the sequence that the model can learn to use as registers. We add these tokens after the patch embedding layer, with a learnable value, similar to the CLS token. At the end of the vision transformer, these tokens are discarded, and the CLS token and patch tokens are used as image representations, as usual. We've found that this mechanism, first proposed in memory transformers, improves translation tasks in natural language processing, NLP. Interestingly, we show here that this mechanism also provides a solution for vision transformers, fixing an interpretability and performance issue. We haven't been able to fully determine why these artifacts appear in DINOV2 but not in DINO, but we suspect that scaling the model size beyond VIT-L and longer training length may be possible causes. In the next section, we validate our proposed solution by training vision transformers with additional register tokens. We evaluate the effectiveness of our approach through a quantitative and qualitative analysis. We also examine the number of registers used for training to ensure they do not cause a performance regression, evaluate an unsupervised object discovery method using our features, and finally provide a qualitative analysis of the patterns learned by the registers. Section Summary. During the training of large models, outliers in the form of high norm patches appear around layer 15 of the vision transformer. These outliers only appear after 1/3 of the training and are observed in the 3 largest models. These high norm tokens contain redundant information and hold little local information, as they are very similar to their neighboring patches. They also contain less information about their position in the image and achieve lower accuracy in tasks such as position prediction and pixel reconstruction. However, these high norm tokens gather more global information and can be used as image representations for classification tasks. To address this issue, new tokens called register tokens are added after the patch embedding layer to store global information, while the original patch tokens and the CLS token are used as image representations. This approach improves interpretability and performance in vision transformers. Section: Training algorithms and data. We've developed a simple architectural modification that can be easily integrated into any training process. We've tested this on 3 different cutting-edge training methods for supervised, text-supervised, and unsupervised learning. Firstly, we used DIT3, a straightforward and robust supervised training method for classifying images using vision transformers, VITs, on ImageNet-1K and ImageNet-22K. We chose this method because it's simple, uses the basic VIT architecture, delivers strong classification results, and is easy to adapt with our enhancements. We applied this method to the ImageNet-22K dataset, using the VIT-B settings. Secondly, we used OpenClip, a powerful training method for creating text-image aligned models. We selected this method because it's open source, uses the basic VIT architecture, and is easy to adapt with our enhancements. We applied the OpenClip method to a text-image aligned corpus based on Shutterstock that includes only licensed image and text data. We used a VIT-B16 image encoder for this. Lastly, we used DINOV2, a self-supervised method for learning visual features. We applied our modifications to this method as it's the main focus of our study. We applied this method to ImageNet-22K using the VIT-L configuration. We evaluated our proposed solution by training models with additional register tokens, which helped us eliminate artifacts. To measure this effect quantitatively, we examined the norm of features at the model's output for each model. We found that when training with registers, models didn't show large norm tokens at the output, confirming our initial qualitative assessment. We also wanted to ensure that the use of register tokens didn't affect the quality of the feature's representation. We ran linear probing on ImageNet classification, AID20K segmentation, and NYUD monocular depth estimation. We found that when using registers, models didn't lose performance and sometimes even performed better. We also studied the impact of the number of register tokens on local features and downstream performance. We trained DINOV2 VIT-L 14 models with 0, 1, 2, 4, 8, or 16 registers. We found that the visible artifacts disappeared when adding at least one register. There seemed to be an optimal number of registers for dense tasks, and adding one brought most of the benefit. On ImageNet, however, performance improved when using more registers. In all our experiments, we used 4 register tokens. We also tested our method on recent unsupervised object discovery methods that rely on the quality and smoothness of local feature maps. We found that adding registers for training improved the unsupervised object discovery performance. However, the performance of DINOV2 on VOC 2007 still didn't match that of Dino, but the model with registers showed an improvement. Section Summary. The authors propose a simple architectural change to training algorithms that effectively removes artifacts from local feature maps. They demonstrate the effectiveness of their approach by applying it to 3 different state-of-the-art training methods for supervised, text-supervised, and unsupervised learning, and show that models trained with register tokens do not exhibit performance regression and even sometimes perform better. Additionally, they find that the number of register tokens has an optimal value for dense tasks, and adding at least one register significantly improves the quality of local features. Furthermore, the proposed method improves the performance of unsupervised object discovery methods when applied to modern backbones. Section: Qualitative Evaluation of Registers. In this final experiment, we're taking a closer look at the behavior of register tokens. We're curious to see if they all behave the same way or if there are differences that naturally arise. To do this, we're mapping out the attention patterns of class and register tokens to patch tokens. The results, shown in Figure X, reveal that register tokens don't all behave the same way. Some of them show interesting attention patterns, focusing on different objects in the scene. This wasn't something we forced, it just naturally happened. We're leaving a more detailed study of register behavior for future research. Now, let's talk about using pre-trained neural network models to extract visual features. This approach has been around since the AlexNet CNN model was pre-trained on ImageNet-1K and has been improved upon with modern architectures like ResNets and vision transformers. These models can handle different types of data during training, and are often trained on label supervision or text supervision. This makes them powerful tools for a variety of tasks, including detection and segmentation. However, the biases in the datasets used for training aren't well understood, and these biases can influence the models that are learned. An alternative approach is to let the models learn from the data themselves, using a task that requires them to understand the content of images. This is known as self-supervised learning. We've been focusing on this approach, specifically using the DINOV2 method, which is great for learning local features. We found that while DINOV2 performs well on benchmarks, it does have some undesirable artifacts. Correcting these artifacts can lead to even better performance. Interestingly, DINOV2 is based on Dino, which doesn't have these artifacts. We've also found that these correction techniques work well with supervised training methods, as we've tested with DET3 and CLIP. Let's now discuss the addition of special tokens and transformers, a practice that became popular with BERT. Most methods add new tokens to provide the network with new information or to gather information. These tokens can be used for classification, generative learning, detection, or for accumulating information from multiple sources before decoding. However, the tokens we're adding don't provide any new information and aren't used for any specific purpose. They're just registers where the model can learn to store and retrieve information. The memory transformer, which is similar to our work, uses memory tokens to improve transformer models, enhancing translation performance. However, we found that these tokens don't transfer well across tasks. Instead, we're using additional tokens during the pre-training phase to improve the features obtained for all tasks downstream. Our research has revealed that memory tokens naturally appear in vision transformers and can be used to isolate existing behavior, avoiding unwanted side effects.